All right. Welcome back. Temperature and phase changes. So when you go from a solid to a liquid to a gas, those phase changes, you're going to be adding heat to your substance. And so since you add heat to your substance, your temperature will increase. These are all our blanks. So your average kinetic energy will increase. Those are synonyms. Molecules are moving faster, which results in the weakening of intermolecular attraction, so you have a phase change. When you go from a solid to a liquid to a gas, you're absorbing heat. It's endothermic. So energy is absorbed. Entropy or disorder will go up because molecules are going to be moving apart. In the solid, they're very close together and packed. In a liquid, they're a little bit looser. In a gas, they're all over the place. The opposite is true. When you go from a gas to a liquid to a solid, when you're removing heat from the substance, your temperature will decrease. So average kinetic energy will also decrease. Those are synonyms. Molecules will move more slowly, which results in the strengthening of your intermolecular forces. And so that's when your phase change occurs. This is exothermic because we're giving off heat. And when you go from a crazy gas to a funky solid to a funky liquid to a straight-laced solid, orderly, entropy will decrease. You're becoming less and less disordered and more orderly because our molecules are held together. So we have this diagram. It's to the back of your notes. I don't know exactly what page, but it's towards the back. So if we have a solid up top, liquid to the side left, and gas to the side right. So if we go from a solid to a liquid, that's called melting. If we go from a liquid to a gas, that's called boiling. That's a G. Sometimes it's called vaporization. Then there's another, there's another one, which is solid straight to gas, which we'll talk about later. This is called sublimation. Okay, stay tuned for more on that. When you have a gas going back to a liquid, this is called condensation. When you have a liquid going to a solid, this is called freezing. Sometimes it's called solidification. And when you have a gas going to a solid, that's called deposition. When matter is changing phase, the blank is blank until the phase change is complete. The temperature is constant. Okay? Temperature is constant. All right, so this is a very important diagram. This is called the phase change diagram. It's towards the back of your notes as well. So notice we have time on our x-axis and the temperature is on the right. We don't have any numbers on temperature, so we can't really be quantitative, but we can be certainly qualitative. So this is a heating curve of a substance. Okay. When you start at the beginning, you have the lowest temperature possible, and we're adding heat because it's a heating curve. So as you go, this is the solid phase. I'm just going to draw a little solid. And this solid, notice how the line as you heat increases. So this is an increase in temperature. It's also an increase in average kinetic energy. Okay? This is also going to be, potential energy is going to be constant during this increasing line time. So during this time, we have a solid being heated. Notice how the graph is increasing on temperature. So we have a change in temperature. We said that. So we are going to go quickly back to reference table T, reference table T. We're going to go to the heat formulas. And we are going to use the formula Q equals mc delta T. This is going to be the formula during any one phase of matter where there's a change in temperature. And so if we go back to our notes, thank you, you go back to your notes, you see we have one phase of matter that's increasing temperature. So if you were to be given numbers on your y-axis, you could calculate heat. And remember, from the beginning of the year, Q is heat. So anywhere along that increasing line is going to be Q equals MC delta T if you wanted to calculate how much heat was being absorbed. All right, then you're going to notice that eventually you're going to have the temperature remain constant. As time keeps going, we keep recording the same temperature. This is weird. So during this second part, this first flat line, there is no change in temperature. It's constant. However, the graph continues. So we have an increase in potential energy. So, gee, if I was going to think about this, we've got a solid, but it's changing. This is a solid going to a liquid. If we were going to read it from right to left, it would be a liquid going to a solid. But this is something called phase equilibrium, which we'll get to later. But notice how there's no temperature change. How could I figure out how much heat is being absorbed during this, which is a phase change? And so if I go over here, I travel over, this would be solid to liquid. That's called the melting point. Liquid to solid would be the freezing point. So if I had numbers here along the y, I could figure out what the melting point was. So how could I calculate the amount of heat it takes to melt something? Let's go back to table T. You are not going to be using that first formula. You're going to be using one of the other ones. We're going to be using this second one called heat of fusion. This is for melting or freezing. So M, again, is mass, Q is heat, but H of F is a constant. H sub F is a constant, and you know, for that matter, so is H sub V. We haven't talked about that yet, but so the heat of fusion constant, let's travel back to physical constants of water. Oh, look, here's the heat of fusion constant for water. It's 334 joules per gram. Heat of vaporization constant, when we talk about that, will be here. If you were heating or cooling another substance, like maybe alcohol or something else, like, I don't know, iron, you'd have to be provided those values. If your word problem does not offer you the heat of fusion or heat of vaporization constant, it's probably because you're dealing with water and you have to look it up. So those are on table B. So back here, along this first flat line, we're going to use the calculation Q equals MHF. If I wanted to figure out how much heat was going to be absorbed when I melt a substance. So after a while, your solid will be completely melted and it will just be a liquid. When I'm going to draw particles a little bit further apart. Notice that once again we have an increasing line, which means our temperature will increase and our average kinetic energy will increase. They're synonyms. But the potential energy is constant. And once again, since I have a change in temperature, if I wanted to calculate how much heat was required to, heat a liquid, Q equals MC delta T. And that formula is found on reference table T. So I'm going to keep on heating my liquid, keep on heating my liquid, keep on heating my liquid, and then eventually I notice a flat line. A flat line so that this is where my liquid would go to the gas phase. If I were to read this graph backwards from right to left, it would be gas going to liquid. So that's a phase change too. If I were to, and this is not straight, I apologize. If I were to travel over here, I would see that this temperature is when a liquid goes to a gas. Liquid goes to a gas, this is called the boiling point. When a gas goes to a liquid, that's called the condensation point. And we talked about how that's the same temperature, and we wrote on our reference tables on table S. So during this time, just like before, we have no change in temperature, or PE, or potential energy will increase, because notice how the graph keeps going up. So the graph keeps going, so the potential energy will increase. So we have a Q formula where there's no change in temperature. There's no delta T. But we have a different constant. Here we are back here. We are going to be using Q equals MHV. MHV is for boiling or condensation. And H sub V is a constant. If it's water, you look it back up on the first page, and you'd find that it is 2260 joules per gram. If you're not dealing with water, if you're dealing with something else, you would have to use a different value that would be provided to you. If you were to calculate how much heat is required to boil a sample of water at a certain temperature, and you could look it up and calculate. Finally, we're going to take that, and all of the liquid is going to be gone, and not really gone. It's just going to be in the gas phase. And so I'll just space this out, okay? And so at that phase, increase of temperature, increase of kinetic energy, PE is constant. Sorry, this is very messy. And since the temperature is increasing, if we wanted to calculate anything, it would be Q equals MC delta T. And remember C, by the way. C is a specific heat value. If you're dealing with water, that value is here. There it is, 4.18. However, if you're not dealing with water, it would have to be provided to you, or you'd have to be able to look it up somehow. You wouldn't have to memorize that. That's a heating curve. From solid to liquid to gas, this is all endothermic processes. If you were to read it from right to left, that would be giving off heat. That would be exothermic, but we're not. So that's a lot. Let's quickly talk about evaporation versus vaporization. Evaporation is a phase change that occurs on the surface. It's below the boiling point. It's a slow process. It's a passive process. So when I put some water, on the desk, like I have some spillage, it's going to go away. It's going to eventually become a gas, but it's a slow process because it starts at the top and then it moves on. However, if I was boiling water on the stove, that's also a phase change. It's also liquid to gas, but it's occurring throughout the whole sample. And it's happening actively because I'm providing heat to it by putting it on top of my stovetop. Versus I'm not doing anything, just having a puddle of water, sit on a table. It's going to evaporate on its own. We talked about this. Those are our two formulas. Q equals MHV and MHF. The amount of energy transferred during a phase change. Temperature doesn't change, so there's no delta T. So now let's actually try those formulas. How much energy does 55.2 grams of ice at 0 degrees Celsius need to absorb to turn to liquid water? So there's a few things we need to look here. We see there's no temperature change because there's only one temperature given. And 0 degrees Celsius for ice, which is H2O solid, should be like a ding, ding, ding. It should be like a, yeah, you know this. This is the melting point. So 0 degrees Celsius is the melting point. It's also the freezing point. It's the same. So what is the formula we use between melting and freezing? Well, it's MHF. How much energy? That's Q. That's our heat. Our mass was provided, 55.2. The heat of fusion constant for water is 334 joules per gram. 334 joules per gram. So all you do is multiply 55.2 times 334, and you get 18436.8. Q is joules. If we were going to round to sig figs, I would need 3 sig figs. Depends on how mean your teacher is. If I'm your teacher, I'm pretty mean sometimes. So that would be 18,400 joules with sig figs. How much energy does 65.1 milliliters of steam at 100 degrees Celsius need to release in order to form liquid water? Use the density formula to find mass. Because I didn't give you the mass. I gave you milliliters, which is volume. So the density of water is 1. So that should be pretty straightforward, 65.1 grams. So now, 100 degrees Celsius for liquid water and steam. That is heat of vaporization. We know it's not Q equals MC delta T because I only have one temperature, and I would need 2 to subtract to find a delta or change in T. So Q is our heat. Our mass is 65.1 grams. The heat of vaporization constant for water is 2260 joules per gram. If it was not water, you'd have to look it up some other way, or it would be provided to you. 65.1 times 2260. Q equals 147126. So if I were to, and this is joules, if I were to round to sig figs, it would be 3 sig figs, so 147,000 joules. Not so bad.